US Concrete, I believe, are on this call as well. So I can tell you a bit more about that later on, but my job today is really just to kind of fill you in on some of the origin sources for carbon in concrete and just set the stage for Teck and Michael, who will get into a bit more of the details in terms of what that might mean for you locally and then professionally. So you may not be aware, but concrete is the most abundant man-made material in the world. So after water, it's the material you're most likely to encounter anywhere across the globe. And that's due for a couple of reasons, but primarily, you know, concrete's just a really fantastic product. So it's really versatile, you know, it does things that no other material can do, and it's really great. And there's a reason why we use it, and there's a reason why we're going to keep using it. So part of that popularity, though, means that, of course, you know, there's an impact. Everything we do as a society means impact. And of course, when you look at kind of that ubiquity of concrete, you're looking at a fairly substantial carbon impact. And when you look at on an annual basis, the amount of emissions that arise from the cement and concrete sector are somewhere in like the 6, 7, 8% range. So after oil and gas and you know, with steel, those tends to be the larger sources of industrial based emissions across the globe. Then as well, for any new building, concrete is going to be one of, if not the largest contributor to embodied carbon, depending on the choices you make and depending on the materials that you have in the building. So when you look at how concrete is made, might not be something you spend a lot of time thinking about. This still mystifies my parents, but it's something that I just wanted to go through here as set the basis. Concrete really originates from the natural world. And so it starts off as limestone in a lot of respects, which is, again, a natural material that we are mining from different areas in the country. And limestone from a chemical perspective is known as calcium carbonate. Other materials like clay are mined from quarries, and they're ultimately taken to cement kilns where they are crushed and heated up and processed. And that's occurring at a really high temperature of 2,700 degrees Fahrenheit. And that process itself is quite carbon intensive, which I'll explain here in a second. And then, of course, once you have cement products, you can make the great material we're here to talk about, which is concrete. And that's probably the thing that you're most familiar with seeing is these trucks on the road coming from Vulcan and Superior and other local producers. And that is being something that is ending up ultimately at job sites. So for those of you who are on the development and design side, you know, you will see these trucks arriving, pouring the concrete, and then that's ultimately what we have to live in, work in, play in, that structure. So looking at that kind of outline, if you want to understand carbon with concrete, you really need to think about understanding cement specifically. So as much as 80 to 90% of all carbon emitted in the manufacturing of concrete really occurs in that second stage, the cement manufacturing stage. That number can be lower. It really depends on a lot of regional factors, but generally speaking, cement is always the largest source of carbon inside of concrete. So one analogy to think about, you know, there's kind of a tired analogy that gets used is that if you want to distinguish cement and concrete, cement is more like a sugar or a flour, and the concrete is more like a cake or the end product. So keep that in mind. Cement and concrete aren't the same thing. They're commonly confused, but cement is really a constituent material of concrete. So, sorry, looking at that kind of breakdown, if you could go back one slide.
Can you all please try and mute your phone?
So looking at that constituent material breakdown of concrete products, if you look at it from a mass perspective, which is shown on the left, what you can see there is, you know, it's primarily mostly aggregate. So that's sand and stone and the other kind of solid materials that give concrete its bulk. With cement being the next largest ingredient, somewhere in the order of 10 to 15% of the weight, and the rest of it is water and some entrapped air typically. So, you know, most of the weight itself is coming from those physical, like crushed stones and aggregate materials, and cement is a smaller material. But the cement is the key thing, because that's what the glue that holds the concrete together. And then again, as I was saying, if you look at it not from a mass perspective, but from a carbon impact perspective, you can see on the right in that pie shape there, that cement really is, again, that 80, 90% of the emissions, where the aggregates typically are fairly small, and water and air, you know, being inconsequential. So looking at how cement is manufactured, this is kind of a step-by-step process. I'm not going to get into the details of this, but just to kind of give you a sense that this is a pretty complicated thing to do. And again, looking at those raw materials that are mined from quarries, they get crushed, they get ground up, they are heated up, they are put into the kiln, and then eventually there's some processing that occurs to grind it down into the powder material that is needed by the concrete producers to make the product at the end of the day. So that's just kind of a layout of that industrial process. It is fairly complex. If you've ever driven by a cement kiln, you'll be familiar with the huge stacks you see there. And of course, there's a lot of emissions coming from that. So looking at that process, so I want everybody to have an appreciation for just how challenging it is to decarbonize this sector. So, everybody, we all want simple, straightforward solutions to getting to a low carbon future. But I want you to understand that when we talk about cement in particular, this is not an easy thing to do. And the reason for that is that unlike a lot of other sectors, where if you could just switch to a green power source, like you might be looking at pretty significant carbon reductions right off the bat. In this case, when we talk about cement, we're talking about a process problem. And the process problem is that everybody wants cement products to be used for construction, but what they don't, acknowledge or realize is that to get to that product, you need to actually manufacture CO2 as a byproduct. And what's being shown here is, I referenced that cement, a lot of the origins of that are limestone or calcium carbonate. When you heat that up under pressure in a kiln, you end up getting a split in that molecule, which leads to the production of calcium oxide as one half, and then pure CO2 as the other. So for every pound or every ton of cement that gets manufactured in the United States, somewhere in the order of 1.04 tons, or like a 1-to-1 ratio of CO2 is manufactured. So that's something to consider for all of your projects. Every pound, every ton of cement that gets purchased, that's the direct impact associated with that material. So again, this is like an interesting challenge. It's a unique challenge. So keep that in mind that, cement producers are doing a lot of things, but this is a fundamental chemistry question, not so much like a judgment or choice question. Once you have cement products, of course, then, you get the rest of those materials I was showing in that previous image of the other constituent materials of concrete, the sand, the stone, the gravel, water, different admixtures, whatever it is that you need to make the product. And then ultimately you have concrete. Let's switch tactics here and talk a little bit about, what is the carbon content of concrete? What do we actually know about that? And if you wanted to make decisions around carbon content of concrete, what would you actually have to do? So that may sound like a basic question, but it's actually quite complicated because we're looking at materials and trying to say like, okay, this is how much carbon is inside of it if I wanted to make a decision based off of that. And the answer here is there's new tools coming on the market around life cycle assessment and environmental product declarations that are really meant to try to answer this question. And the easy analogy to this is if you go to the grocery store, right, you might be looking on the back of a carton of milk and it might say something like, oh, there's this many calories or there's this much sugar or this much fat on the back. And that's meant to help inform you. These products are meant to do the same thing, except around environmental impacts of materials. So for those of you who are involved in LEED, this is old news. You don't need to hear me tell you about this. But in general, these are tools that are meant to quantify the impact. And they do that using a really complicated set of assumptions around, what the energy sources are, where materials are sourced from, how far they have to travel to job sites. There's lots and lots of different assumptions that are built into it. And at the end of the day, they spit out these estimates that are shown here on the screen, which are, how much energy was involved in manufacturing this material, how much carbon is there in it, and other kind of environmental impacts we might care about, such as acidification or eutrophication or other things like that. So these are becoming more common. And because concrete is such a variable material, there are a lot of EPDs that are being generated for concrete. But I would say, there is work to be done still in improving these, but they do exist on the market in some respects, more commonly on the West Coast so far, but growing in availability kind of across the board. So what you would do with those EPDs if you wanted to know the carbon content of your product or your project, I should say, is you would look at, again, the material quantity you're talking about. So let's say you're buying 10,000 cubic yards of concrete. From the EPD provided from the producer that the average kind of, carbon content of that material is X. And you would multiply those two things together and add them to other calculations for other materials. And then you would get your whole building estimate for the carbon content of that. So the key thing to consider here as well is, we're talking about embodied carbon. We're really talking about a comparison or a comparative analysis, because at the end of the day, you're basically quantifying what you're not doing or what you're not producing, right? So how do you measure a negative? To do that, you have to have a baseline. So that's something to consider here as well. Is when you look at EPDs, the question isn't really, what does that EPD say? It's what is the differential between that EPD versus what an industry average would look like or a local average would look like. And the difference is really what matters here. That's the reduction. So I hope that makes sense. But again, it's not so simple as just measuring it and saying like, that's the answer. You have to compare it to something. And in a lot of cases, understanding what a good baseline is also somewhat confusing or challenging, depending on the local data available. So, I mentioned a couple of reasons why concrete might have a fairly impactful level of carbon associated with it. I don't want you to get to the impression that concrete is a bad material from a carbon perspective. I think, some of the fantastic things that concrete does are things like reducing thermal mass heat transfer. So if you're looking at things like long-term durability or resiliency, or looking at energy efficiency, concrete is one of the best materials out there for all of those things. So again, part of why it is used so frequently is because it does all of these performance attributes extremely well. And in addition to that, although there is a carbon impact, it's not like we're talking that it's astronomical scales different versus other materials. So this graph is coming from a life cycle analysis conducted several years ago, where they're looking at the potential impacts of different materials. And what they're showing you here is that, although concrete does have an impact, especially cement is being much higher. If you look at things like plastics and steels and glass, it's not really that far out of the realm in terms of what's happening. They're fairly comparative. And the real challenge here, I think the question people kind of ask, again, looking for a simple answer is, should I just build everything out of wood? Should I just build something out of steel? Should I build it out of concrete? What is the easy answer here? And I think what I would like you to consider is that that's actually the wrong question. Asking which material is better on a carbon perspective like this is not really a good way to think about it. The better way to think about it is that all of those materials are going to continue to be used everywhere. We're going to need all of them. And the question is, how can we do better across the board in each and really drag kind of the carbon content down for all of them using different strategies? So it's not a material substitution question, because we simply really don't have enough of each material to do all of that. And in some cases, they have specific applications where you can't make material switches. So it's really more of a question of what can we do for each. So getting back to that question again of like how much carbon is in concrete and why that's a challenging question is that you might also not have thought of this, but almost no two concretes are alike in the sense that you can have concrete of the same strength, but it has different purposes. So it will have different characteristics intentionally. In the same way, again, back to that cake analogy, like you can take flour and butter and sugar and you can end up making cookies or cakes or bread. Like you can make a million different things out of that. And that's also true of concrete, is that depending on the ratio of materials, depending on the desired outcome, you can make all sorts of different kinds of concrete. And so that's a key thing here, is that there is no universal constant here. CO2 in concrete is complicated because you have to look at each product and say, like, this is different from the other and this is what the impact is. So all of the factors that I have listed on this slide are things that would affect the potential carbon content of concrete. A lot of that has to do with the amount of cement required. So if you look at things like the strength of the concrete you're looking for, if it has higher strength, it will have more cement, therefore it will have a larger carbon impact. Also looking at things like quality of aggregate materials. So some local sources of aggregates are just better quality, so you need less cement for that purpose. In other cases, you're looking at things like replacing cement. So if you're, Teck's going to speak to this more directly in terms of some of the materials out there, but you can actually replace certain percentages of cement with other materials. Also just looking at where materials come from. So if you are buying your products from Turkey and shipping them into the USA, that's going to obviously have a carbon impact associated with shipping those materials to the site. Similarly, if you're driving to a remote site, all of those trucks on the road do have impacts as well. Finally, there's other kind of things you can do that will tweak the edges of the carbon impact, such as just different admixtures that help with different features of concrete. Looking at energy efficiency at the actual facility itself. So newer facilities are generally more energy efficient, so they have a lower impact of production. And then of course, things like if you are running on green energy, if you're running on solar, wind, nuclear, things like that, you're going to have a lower carbon impact than if your local power grid is running off of coal. And finally, something CarbonCure cares a lot about is this concept of new technologies that are emerging that might help further reduce carbon in concrete. One other thing to consider here is that when you look at carbon content of concrete, it's not really a full picture, because typically most of the information out there from life cycle assessments are looking at kind of the first three phases of product stage. So as shown on that chart there, you're looking at raw material sources, you're looking at transportation, and you're looking at the manufacturing phases. it doesn't really take into account things like waste disposal or life cycle kind of total emissions issues. So that is something that to consider, is that most EPDs also only really report things that happen before the concrete arrives on the job site. And again, of those three kind of sections there, manufacturing is the vast majority of where those emissions come from. So what does an EPD look like for this industry? And thank you to Teck for providing me with this example, which comes from Vulcan. So this is a local source from Shirlington, Virginia. And what you can see is that this image here is showing you that this EPD is specific to Vulcan's plant at that location. At the concrete strength, you can see there's a line that says compressive strength of 5,000 PSI measured at 28 days. And that the unit, again, is on a per unit basis of 1 cubic meter. So that is one thing you'll notice about EPDs too. They tend to use the metric system. So if you're used to thinking in imperial, just be aware that most EPDs are metric. And being Canadian, I appreciate that, but I know sometimes it's not so much appreciated in the US. And then down the line there, you'll see the text is really tiny, so I won't ask you to read that, but you can see that, you know, the first one on the list is global warming potential. And in this case, what you're seeing is that from this particular mix, the per cubic yard carbon content is 274-ish kilograms of CO2. So for every cubic yard, that's about the impact of CO2 coming from this mix. One other thing I mentioned, you know, I talked about the importance of baselines and comparisons. So like, what does this mean for this EPD? You would, in this case, really want to compare it to some other baseline concrete mix out there and see, you know, how much lower this would be from a standard practice. And so I do owe a lot of the content in this presentation to the Ready Mix Concrete Association. And if you're not familiar with their work, I'd encourage you to check out their website, which is the nrmca.org. They do publish EPDs for a number of different producers in their database, and they do publish industry averages as well. So if you are someone who's interested in looking at EPDs, their EPD program is going to be a wealth of data for you that I'd encourage you to check out. And I do know, as Kirsten said, the CLF has also done a good job of drawing attention and making connections with the different EPDs that are out there. And if you're familiar with the embodied carbon in calculator from the EC3 tool, it also pulls this information for you as well. So again, beyond, you know, the specific industry averages, a lot of producers out there, obviously like Vulcan here, have prepared facility-specific EPDs. And one thing to consider too is that when you talk about concrete, as I was saying, like you can take those same sources and make 1,000 different mixes. One challenge for EPDs in this industry has been, you know, how do I make EPDs for every mix that I have? It's very labor intensive, it's costly. And then if I make a decision like, oh, I'm going to change where I buy my aggregates from, or I change the cement that I use, I have to throw all that EPD out, right? It's not useful anymore because I've changed my source of supply. So there are tools that are being developed that will allow producers to make more of these EPDs on demand. So basically you could say, you know, I'm using this source and I'm using this material, and the person who's wanting to buy this from me has a specific strength in mind. I can actually generate that estimate in real time. That is not a free thing for a producer, but I just wanted to let you know that, you know, there are, again, evolutions of this that are coming out to help answer the question for concrete specifically. And just again, referencing the Ready Mix Concrete Association, like this is an example here of what the industry average looks like. So I think Teck's example there was showing you that for that 5,000 PSI mix, that it was something around the order of 270 kilograms. In this case, what the National Ready Mix Concrete Association is showing us is that 5,000 PSI mixes typically range between 316 and 522 kilograms. So you're seeing the minimum and maximum there on the left. So, you know, the industry average is taking into account different producers in different regions that have different energy grids, that have different kind of standards and practices. But then the key thing about this I wanted to show you as well is that if you look at the top here, the labeling is kind of hard to read, so I'll explain this for you. But if you see here again, like if you look, there's one that says 4001-5000-00, FASL. In this case, FA means fly ash, and SL just means steel slag. So those are, again, cement replacements that Teck will speak to. But what that's showing you is that that is a standard mix that only uses cement. And what it's saying there is that that mix should be somewhere in the order of 522 kilograms of CO2 per cubic meter of concrete. What you're seeing as you go down the list, those numbers go down. And as you're seeing on the labels, the next one says 4001-5000-20-FA. that means that this mix has 20% fly ash replacement of cement. And you can see that that one has something in the order of 60, 70 kilograms less CO2. So again, that's just showing you that the more cement replacement you make, the greater the reduction in CO2 on average. And that again points to the fact that cement really is such a defining factor here, that you can change 20% of the content and get a 60, 70 kilogram reduction in CO2. So I talked to you a lot about what is today, what the reality is, where we are, some of the ways you can think about carbon and concrete. But I wanted to spend a few minutes here talking about tomorrow or the future. So one thing to understand again with concrete is that, you know, just switching to green energy is not going to solve this carbon problem. The industry has a much greater challenge. And a lot of that comes from the fact that process-based emissions, that manufacturing of cement makes just a lot of CO2. So what this chart is showing you is that some of the traditional strategies like, you know, energy efficiency or switching of fuels to greener sources, those are showing you that those strategies are actually going to only accomplish a minimum amount of carbon reduction. So even if everybody was running on, you know, pure wind power, you might get a 15% reduction or so in the carbon impact of concrete. It's really the two strategies at the top that are going to be the most influential. And those two things, I'll start with the one that's the darker orange, which is labeled as reduction of clinker to cement ratio. What that means is, again, that replacement of cement with other materials like fly ash or slag. So what that is saying is that if you really want to achieve a lot of decarbonization, you need to find a way just to use less cement. The trick there is that we don't actually have enough materials like that to have a global scale of replacement at the level needed. But that's a lot of research is underway in terms of finding different materials or additional material sources. And I think Teck will speak to some of this too, where you can actually replace cement with different materials and get high replacement percentages. So that's expected to be a pretty significant source of reduction, again, focused on just reducing the quantity of cement in the mix. The top one, the lighter orange, is what they call carbon capture, utilization, and storage. So you may not know that term. If you do know that term, you might be thinking of some of the news around people capturing CO2 and kind of pumping it underground and just storing it in a big kind of oil and gas former reservoir. So that's the same concept, but the idea here is basically, can we divert CO2 that has to be manufactured and keep it from entering the atmosphere, either by putting it somewhere where it can't do any harm or using it to make new products? So that's really the key thing here. What you should know about concrete is that it has a unique ability to do this. So among all building materials, concrete has this unusual and really potentially attractive capacity to take CO2, absorb it into its structure in a beneficial way. So this report coming from the International Energy Agency is basically saying that half of all emissions reductions in this sector are going to come from some new way of capturing CO2 and placing it into concrete. And that's what's going to be necessary to reach some of the reduction targets that have been set. So not all of those technologies exist today. Many of them are being researched. You know, not all of them are economically viable, but I just wanted to let you know that as well, is that there's concrete could be in the near term future a major solution to carbon reduction because it actually has the ability to bind carbon into its structure and lock it away for hundreds of years. So I spoke a little bit about, you know, fly ash and slag, and I just wanted to kind of talk a little bit further about some of the cement alternatives out there. So looking here, you can see all these very nicely colored, nicely hued powders. So anybody who gets excited about chemistry, you know, this is all the good stuff there. You can see that some of the names up there, the typical ones, of fly ash, so FA, furnace slag, silica fume, others that are used. But there are also emerging new materials that are being investigated that could do the same thing. And what these materials do is they basically act as a substitute for cement. So again, they just replace it typically at a 1-to-1 ratio in the mix, and then you would see a corresponding reduction in cement. These materials are referred to pozzolans or having pozzolanic properties, and they generally react with calcium hydroxide coming from the cement to provide cementitious properties. Just as a key thing here though, these materials aren't like fully benign. They can have other effects on properties such as set time. they can affect coloring, they can affect other properties of concrete. So they're not something you could just kind of switch on and off and expect it like nothing to be different there. But you know, they are products that are available and are emerging. So some of the ones that are growing for new demand, there's a new kind of company in New England that is focusing on producing ground glass materials that could theoretically be used this way as well. Other ones you hear talked about are calcined clay and metakaolin. So there's a few other materials that are being explored. But this is also goes all the way back to, you know, ancient Rome, where some of the first concrete was made using volcanic materials. So that same activity is what's being tapped into here from a chemical structure. They're just coming from different source points. So going back again to that carbon capture, utilization, and storage topic, this just shows you some of the examples of how that might work. And what you're seeing here again is if you're looking at an industrial CO2 production source, you can either just take that and jam it underground, which is called, you know, this sequestration or storage. And that's typically done in former oil and gas reservoirs. You can also take the CO2 and use it for other purposes, which are shown in the red and the green text. And again, the most interesting one for concrete is the one at the very top there, which is listed as mineralization. So that just means converting that CO2 into a solid mineral as part of concrete materials. So another thought I wanted to raise looking at the audience on this call is that, you know, everybody is interested in lower carbon products generally, but I want you to consider that it's not necessarily just a technical problem. It's not necessarily just a technology problem. It is in a lot of ways a behavioral and structural challenge. And this is built into just how we design and build buildings. It's a problem that we know of for all sorts of different reasons, everything from, you know, cost efficiency to stakeholder engagement to, you know, all these different kind of things that exist as a problem when you have 4 or 5 different players at the table and a very defined sequence of events that occurs for traditional design bid build projects. So some of the challenges that exist if you're a concrete producer that affect people like Teck as they do their work is that a lot of engineers may have specific prescriptive requirements that call for necessary levels of cement to begin with. That's also true in the public sector. There may also be pressure for high speed. So if you're building a multi-story building, every day you have a worker on site is costing you money. So in a lot of cases, people make the choice that just putting in more cement to make the concrete strength rise more quickly is cheaper than hiring more people. And then looking at this disaggregated responsibility. So we all play different roles. And finally, you know, carbon is not really built into the cost budget balance sheet there. So it's not really considered the same way other costs are. I'm going to quickly touch on some public policy side, and I'm going to pass it over to Teck. I think I'm probably going a bit long on my time here. But looking at local governments, one thing that's come out of this is that people are starting to look more consciously about what the choices they're making. And this is a study that I'm referencing from the city of Portland in Oregon, where they are basically saying that if they looked at their different mixes they use just to make sidewalks. And what they found was that they could cut up to 25 to 30% of the carbon content of those mixes just by simply changing how they ordered it, how they specified it, how they asked for it. And they didn't have to do any new real kind of evolutionary things here. They didn't really pay more for it. It was just a question of choice. So again, if you are on the public side of the equation, just be aware of this, is that a lot of the time, you know, we do things because they're simple and no one's really kind of gone back to look at why things are done the way they are. When you look at it, you can uncover that, hey, you know, there's actually a lot of things we could be doing to make this more carbon efficient without affecting price, affecting schedule, or things like that. And that's really important because government actually directly or indirectly buys 40% of concrete made on an annual basis. So most concrete is actually going to things like parking lots and foundations and, you know, sidewalks. It's not going into 12-story buildings. And that's, again, the 2 biggest drivers for any concrete producer in terms of production are typically new housing or new building starts, and then government infrastructure spending on things like bridges and, you know, sidewalks and just infrastructure renewal. And if you do want to learn more about kind of the current evolving policy discussions, I'd encourage you to check out some of the work that's ongoing. So states like Washington, New York, New Jersey have proposed legislation that would push for state agencies to consider carbon in their procurement of concrete materials specifically. Other states are looking at doing this, you know, for all construction materials, but these ones here are probably the most advanced and the most sophisticated. And if you look at these ones, they're referred to as New York Senate 542 and New Jersey Assembly 5523. these push for consideration of carbon in all state purchases of concrete. And thank you.
Thanks, Eric. That was a really great perspective. I really appreciate the analogy on baking a cake. Look at EPDs as calorie intake for the future from now on. Does anybody have any questions for Eric before we move on to tech? We can also address a Q&A in the end. Okay, great. Well,
good morning, everyone. Like I was introduced, I'm Teck Chua, Director of Technical Services with Vulcan Materials, the concrete side, not the aggregate side. Before I start, today is February 12th. Is actually the first, the new year, a Chinese New Year for people, over 1 billion people in the world that celebrate Chinese New Year. So I just want to give a shout out to them. It's the year of the ox, so 新年快乐，恭喜发财. So with that, let's go to the next slide. So my presentation is going to be relatively short compared with Eric because, what's in the concrete producer's toolbox is really very limited. Not a whole lot to talk about. But what we're aiming for, as Eric has laid the groundwork, is there's a lot of CO2 generated through the production of cement. So the key principle here, what we're trying to do in concrete is to try to use as little cement as possible. So cement avoidance is the key word. And the strategy available to me as a producer in DC area is really simple. It's trying to use more of the other cement substitutes. The ACI call it secondary cementitious materials, SEM. So far on the list is slag cement. Is used to be known as ground granulated blast furnace slag. So it's the same thing. Fly ash from coal burning power plant. We still have some of those power plants around here, but mostly it's coming from outside the area, really. West Virginia being one, Pennsylvania, in the coal countries. We got a plentiful coal ash from those areas, but it has to be trucked quite some distance. Then the third one is adding carbon dioxide. Basic carbon dioxide is really what we know is dry ice. And we can use that using the great technology that CarbonCure has come up with, and we'll do that. And lastly, I'll talk a little bit about other specialty materials that are available to me as a producer. So that's sort of an overview of what I'm going to talk about. Next slide. All right, Eric also talked a little bit about concrete, and so let's talk about concrete 101. And concrete is really simple. It's adding cement, adding aggregates, adding water, adding some admixtures, and that's all. That's really simple. I mean, you can mix this up in your backyard if you choose to. You can go to the home improvement stores like Lowe's or Home Depot, buy yourself back cement, and get some aggregates maybe from Vulcan, and then voila, you can go to town with it and mix up your concrete for your patio or whatever if you choose to. But it's gone from a modern ready-mix producer in a big metropolitan area like DC is from that very simple formulation. It's gone pretty sophisticated. Under each material ingredient, we have different items that we can use. Like for example, under cement, SEM we talk about, and Eric has shown some of that in his earlier slides. And then aggregates, you can get crushed stone, you get manufactured sand, get washed gravel, natural sand, recycled aggregates, like, taking concrete that is coming back to our plant for leftover concrete that come back from the project. People ordered 10 yards, they only use 7, and we got 3 yards coming back. What do? We can turn that concrete into, crush it up, and that becomes a good recycled aggregates that can be used and put it back in concrete. Then water, we got this processed water that whether we wash down a mixer or and that's primarily in a plant. That's a primary source is when we're washing a mixer, and we got to discharge that water somewhere, and so that water contains cement slurry and so forth, and we have to process that water, and that water can be used and put it back in concrete. And so environmentally, that's rather attractive. You don't have to discharge that water outside their properties and so forth. Then admixture is just the admixture manufacturers is really they are the one that leads the advancement of concrete technology. They come with all sorts of stuff. You can make concrete set faster using accelerating admixture, make it set slower, hold it for a day or a week, or a month if you want to. And they have the chemical available to do that. Then you have water reducer, then another more potent form of water reducer called high range water reducer. Formerly go by another name called super plasticizer. They make concrete very highly workable and so on and so forth. So it goes on, and it's not an exhaustive list. Next slide. All right, Eric's shown you this excerpt of a table from National Ready Mix. Let me, being Americans, I prefer the imperial units. So what is shown here is actually kilograms per cubic yard in terms of embodied carbon instead of cubic meter. It's the same. We happen to pick the same class of concrete. But if you're looking at, again, Eric has referenced this as well in terms of the GWP reduction by adding different amount of fly ash or slag. And one thing that's not shown on the slag side, we can actually go up to 75%. And as you see that from 100% cement, use that as a reference, is look at the percentage reduction in GWP all the way to close to 60% reduction using as much as 75% slag cement in the concrete. So next slide, please. Okay, I want to give you a little bit of details about what each of these materials is. So for those who are unfamiliar with it, so we'll start off with slag cements. Slag come from the steel or iron refineries. So when you take iron ore and melt it to refine it, you have a lot of impurities in that iron, and that impurities is going to float on top of the molten iron. And that's really the scum that's floating on the molten iron, and that's slag. And you divert that slag, separate it from molten iron, and then quench it with water, meaning pounding lots of water on it. Somebody was saying to me that they pour like 10,000 gallons of water per minute, 10,000 gallons per minute of water on that slag. And what you got, rapid quenching produces a glossy material, and in the process, what they produce is a very small glossy granules, and then they'll take that, drain the water off, and then put it in a grinder, wall mills actually, and grind it into grain sizes that are smaller than Portland cement. So that's what you get, slag cement. Next, please. Just a little comparison of sort of explain why slag as a secondary cementitious material is not as reactive as Portland cement. One of the chemical compound that we look at is CaO, or calcium oxide. And with slag, it's somewhere, this is coming from ACI, is ranging from about 32 to 45% depending on the source. And Portland cement is around, this particular cement is around 62% calcium oxide. That's the more calcium oxide you have in a material, the more reactive it is. Next slide. Okay, so this is one of the higher strength concrete that we can produce, or we do produce. And if you look at the x-axis is the percent of slag ranging from 0 to 75%, and then each line represents the strength at each different age. So we start off with the line of interest. First one is the 3-day strength. Can you click the advance the slide one more? There you go. Okay. And so the 3-day strength, when you have 0% slag, it's breaking somewhere about 7,000 psi in 3 days. But as you can see that as you increase the percent of slag, the 3-day strength continue to drop, and it's by the time you get to a 75% slag mix, it's less than half of the 0% slag mix. So that's the impact that you have on the strength development. But as you look at the other graph, the red graph, that's a 7-day. Then the gray one is 14-day, go to 28-day strength. Once you get past the 3-day strength, you see that strength start to catch up. And by the time you get to 28 days, you actually get an increase in strength when you have more slag in a mix. So it's very interesting. But as you can see there, it is actually the optimum amount is right there between 40 to 55%. Adding more to it actually start to diminish the strength of development a little bit. So you do sacrifice some strength when you go higher amounts of slag cement. Next slide, please. Okay, well, fly ash. What is fly ash actually? So in the coal burning power plants, you burn coal, you're gonna get ash. That ash is gonna fly up the stack. That's why it's called fly ash. And by EPA regulations, emission standards, the power plants have to capture those ash, and they, the various means they use electrostatic precipitator, and then capture all that ash and drop it into a container, various containers. So you got a bunch of containers capture that ash, and so that's what you get, how you get fly ash. There is a companion to fly ash. It's called bottom ash, because those are the ash that drops to the bottom of the smokestack. So very creative names there. Anyway, advance another one, please. Okay, so the coal in the eastern seaboard comes from the Appalachian coal. There's lots of coal and in the Appalachian region, and because of the type of coal, it produces what we call a type F fly ash. It's the ASTM classification, ASTM C618 class F fly ash. So that's only a class F fly is only available in the East Coast. Well, there's another fly ash called class C fly ash. That's more of a mid-east to West Coast phenomena. That's because it's got different kind of coal in that region. So next slide, please. Again, looking at the calcium oxide content, you can see that this fly ash or class F fly ash is very, very low in calcium oxide. 3% is what we're looking at. again, comparing with 62% from Portland cement. So that's not very reactive at all. Matter of fact, when you mix fly ash with water, it's going to stay unhydrated for ever and ever. We have ACI certification classes and stuff like that, and the technicians had to, run through various test methods in concrete and so forth. So one of the things that one of the fake concrete, we call it, that we use is actually just simply fly ash. And after they're done, they can dump that sample back into the pile, and that pile's been there for 10 years, and we keep using it and keep using it. So that shows that how unreactive fly ash. Relatively speaking, slag cement, if you add water to it, is actually going to get hard. Slag and water, it's hydrating. It can get hard, and it can get some significant strength with it. So just next slide, please. So this is another comparison of the percent of fly ash and its impact on strength. And on this, the curve on the left-hand side with 15% fly ash, you know that the fly ash start off, lacking the reference, the 100% Portland mix. But by the time 28 days comes around, it is actually crossover, meaning that fly ash start to generate more strength as you go past 28 days. Now, conversely, if you look at a 30% fly ash mix, you know that the crossover actually doesn't happen until about 70, close to 75 days later. Okay, so that just gives you an idea. If you recall from the strength development curve with slag, and a crossover happened much sooner. So just the behavior of different materials. Next slide, please. All right, this is not going to go into much. We're talking about adding CO2 to concrete. That's the chemical reaction that takes place, and basically we're generating calcium carbonate or really limestone in the process. One of the advantages that Eric didn't mention is that the limestone that is generated is very different from the limestone that cement companies add to the cement when they're grounding their clinker. The limestone that is generated using the CarbonCure process, it's nanoparticle size, very, very small. Okay, so you got, you go from micro and all the way to nanoparticles. And so there's a lot of advantage with nanoparticle size in terms of how it affects chemical reactions in concrete, chemical hydration, and so forth. So I don't want to get into that. It's really, really technical. But suffice to say that the CarbonCure technology permits us to have a form of carbon sequestration, locking up that CO2, but it's locking up forever. Okay? It's for as long as a concrete lasts. So because it's changing into a different chemical compound altogether. It's like going to the cake and flour example. You add flour and bake cake with it. What do? You basically sequester that flour forever and ever, right? And also it helps us in terms of concrete producers to avoid using more cement. Next slide, please. So the pros and cons of the two different materials. Looking at slag cement on the left, it replaces up to 75% cement. That's the typical usage that we do, send those kind of concrete out. The high slag content typically used in mass concrete, where trying to keep the temperature of the concrete within a certain specification limit. Cement, it's the heat generator, and therefore, avoiding cement makes perfect sense. And voila, it's good for generating very low carbon concrete as well. then the cost of slag, cost of slag can be greater than cement. Some of my plants that further away from the slag mills, because the trucking cost is actually, we're actually paying more for slag cement. As far as supply is plentiful, as long as a steel refinery, they're going to have slag. So the slag that we're getting, this glass granule that the slag mills get, it's some come from international sources, some come from domestic sources. There's a slag mill that LafargeHolcim has a slag mill up in outside of Baltimore called Sparrows Point. It used to be Bachelor steel back in the heydays, where Bachelor steel was generating, doing a lot of making a lot of steel and a lot of slag, and the slag cement mill was built there to process those slag. But Bachelor steel is now defunct, went back up, and that steel mill is no longer there, it has tore down, and so forth. But they have a nice harbor there, and so they can import. They also have a rail terminal. So they're reeling a domestic source. I believe they're bringing that slag from Chicago, some of the steel mills that are operating in Chicago. Internationally, they're telling me, right now they're getting the granule from Brazil. I know that I've used slag from Italy, from Turkey, from wherever. Vulcan has also used finished slag from China a few years back. Is actually slag that's already ground in a slag mill in China and came in to Norfolk, and we were using that for a few years. One of the cement companies actually importing for about 5 years. So this is to show you that it's plentiful supply. As far as slag color is white color is very much like white cement. So from an architectural standpoint, it's rather advantageous. And I want to mention the Kennedy Performing Arts Center, which wins the 2020 International Concrete Excellence in Concrete Award, beat out a lot of international competitors. The signature structure there is very white, and it's really white cement plus slag cement in there, and plus other goodies make it gleaming white. But so that's good. Now, for those that might not be familiar, sometimes when you place concrete with slag in there, you can get this blue and green, shades of color that is kind of green and blue. And sometimes I do get calls about that, and people calling me, my customer calling me, hey, the owner is upset, architect's upset, why do we get this color? I want to assure you, and for those who experience that or about to experience that, I want to assure you that that color will fade and completely go away. Sometimes it may take a few weeks, sometimes it take a few months, but they all go away, okay? So it's just a complex chemical, and I think it's a compound, a chromium that gives you that kind of color, but it's not toxic or anything like that. It doesn't last. So going to the right-hand side, looking at fly ash comparison, we can, locally, fly ash has been used up to 40% replacement of cement. The cost-wise is half of that of cement, so it's relatively inexpensive material. The unfortunate part of it, the supply, at least in the short term, is rather unreliable. If the power plant doesn't burn coal, then we don't get it. Locally, we do get there's formerly PAPCO plant. I don't know what they're called now, but down on 301 in Charles County in Maryland, southern Maryland, before it crosses over the Potomac River again. There's a power plant there. Now that's a coal burning power plant, and we get a fly ash there. Unfortunately, that plant doesn't run all the time. It's not what they call a base load plant, so it's not run all the time. It's coal. Coal is not very competitive compared with natural gas. So there's an economic pressure as far as that goes. Natural gas is cheaper, so they can burn natural gas to generate power, and that's what the choice of fuel there. And so similarly, I mean, you know that the government policy is against coal power generation, so there's lesser supply of fly ash because coal power plants are being decommissioned and so forth. The color of fly ash, if it's treated, beneficiated is the term that we use, and it removes the residual coal, and the measurement of residual coal is through loss on ignition. If it's 0%, the color is actually beige or buff color. It's a very interesting color. But if you have some amount of LOI, generally in the 2 to 6%, it can range from a very light gray to a very dark gray. So that's the color of fly ash. And architecturally is something that we need to think about if the architects are concerned about getting a certain color. So next slide, please. The specialty materials that we're talking about is type 1L cement. Type 1L cement's got, it's permitted to have a maximum 15% limestone addition. So you add 15% limestone to the cement, you can use 85% or less in clinker. And so there's a lot of cement avoidance there, significant cement avoidance. Now that's compared with 5% maximum for regular cement that we use. But the cement companies typically don't go to the max. It all depends on cement chemistry and so forth. I mean, at the end of the day, the cement companies want to produce a cement product that has optimum properties that the customer like. So I know locally there are two sources of type 1L cement. They'll range from, I think they're adding about 10 to 12% limestone. They don't go quite up to 15%. Likewise with the regular cement, they don't go to 5% either. They're somewhere in the 2 to 3% range. So like I say, it's available in the market, but as far as getting in a plan, it certainly depends on the project size and stuff like that. As you know, a producer, one of the big constraints that I have in our plan is that we have limited storage capacity. So we got cement bins there. I mean, we got to have enough storage capacity to meet the daily demand. And because, we're trucking the material from, say, 60, 100 miles away, you get tied up in a beltway traffic, and not now, of course. But, you got trucking trucks tied up, and we can only store, say, 3 or 4 loads of cement in a plant, and we got a big pour. We got to be thinking about, the sequencing of trucking materials cement coming into the plant and so forth. And so you got to have capacity for a regular cement. And then if the project requires type 1L cement, we really have to think very hard on what we want to do, because we already have another a couple of bins maybe one tied up with cement and tied up with fly ash, and we really don't have much room left. So that's why we still consider it a specialty material, but it is available for the right project. So next slide, I think I'm done. Yep. Any questions for me before we move on to Michael? Okay, I think we can go to Michael.
Thanks, Teck.
Great, thanks, Teck. My name is Michael Cropper. I'm a senior associate here with Thornton Tomasetti. I'm a structural engineer by training, so everything you hear is my thoughts as a structural engineer and based on my experience and our experience. At Thornton Tomasetti, we've got various practices, and including structural engineering and sustainability. And so the embodied carbon topic really is a good nexus for both of those practices. So following on from Eric and Teck's presentation, I wanted to start to talk a little bit about how this looks on a project and what we can do for specifications. There's as Eric alluded to earlier too, there's only so much we can do with materials, there's so much we can do with innovation, but a lot of it's going to come down to design, approach, just philosophy of our industry and of projects moving forward. That's a much wider topic, and I think that the intent is that this forum will get into that more in coming sessions. But for now, just wanted to start with a discussion of specifications and a little bit of how we've implemented some things recently in our region. So next slide, please. So one of the things that we are seeing more of, and especially with regard to embodied carbon, is this idea that our concrete specifications should be more performance-based, that we as engineers and working with the architect, we know the performance requirements and the constraints and the aesthetics of the concrete that we're looking for. Those requirements should be in the documents. They should be in the specifications, but we should not be setting limits on cement replacement or on water use or other admixture use, because we don't know. We're not the experts. We don't know better. The idea is to have these performance-based specs to remove constraints, to allow innovative products, to allow the use of things like maturity sensors, allow longer cure times. And really the idea is let the experts, let the mix designers, let the producers do their best work, coordinating with the general contractor, with the subcontractors, with schedule, with transportation requirements, placing requirements, finishing requirements. Really open it up to the team to be creative, to go low with embodied carbon. And again, this is once we get to the specification part of a project. There's so much we can do in design and from whatever the project's goals are. But once we're at the specification stage, the idea is remove constraints. Next slide, please. And the key that I put on the right there is that specifications must be biddable, right? You can't just, you can't cross your fingers and hope that you're going to get low embodied carbon concrete from your subcontractors. It's got to be, you've got to set targets. If you're going to give the contractor the freedom to operate, then you need to provide targets and limits to hit. And some of that comes from what can be done in the region, what's the experience, and then can we push to go lower? One of the things that maybe for compliance requirements, you need to require EPDs for each mix. Our current Thornton Tomasetti specifications provide sort of a benchmark average from NRMCA, from the National Ready Mix Concrete Association, for our region, or for whatever region the project is in, to say this is the benchmark. We are looking for a certain reduction. And then the idea is not to impose a reduction on each specific mix, but what is the total reduction that you're trying for in the structural frame? Unless you're in a design build situation where you might want to specify a total embodied carbon reduction for the project as a whole, you're going to be bidding these out to different individual contractors. So it's better to keep concrete within concrete and set those targets per material and per the volume of material on the project. So that gives again, the contractor the freedom to say, well, I'm going to use 70% slag replacement in a mass foundation and get a large reduction in embodied carbon, but maybe in elevated floor slabs, I can't add 30% slag. I can go 15, or I can do 10, or whatever, and then using using the combination, sort of the weighted average, and the overall embodied carbon of the project, you can hit your reduction targets. Next slide, please. And speaking of the targets for reduction, this is really important, and it's something, everything about embodied carbon requires collaboration across the whole team. And it starts from what the project goals are, what the owner's goals are, what the architect wants from the project, how is the sustainability consultant approaching the project, and then how can everyone work together to achieve the vision. And you have to know what's the baseline. Is it a project-wide target? Is it specific to materials? Are we saying, well, 70% of the embodied carbon in the building is in the concrete, so we're gonna try to do what we can for the 70%, and we just don't know enough about the other materials that we're not going to worry about it? What baselines are we using? Are we using Carbon Leadership Forum baselines, which are right now really national averages and may not always be appropriate? Are we using NRMCA regional averages? Is there enough data in EC3 or in maybe a developer's portfolio or our collective project team experience to say, these are the averages we should be hitting for this type of project in the DC region? Is it based on building type? Our experience at Thornton Tomasetti is that it varies widely based on building type. Specialty buildings that aren't really rectangular floor slabs can get very high embodied carbon per square meter versus something that you could do, maybe a residential flat plate building that has a 25-foot grid. You could go lower per square meter. So you have to kind of, it's comparing apples to apples. But the main point that I wanted to make was that the project goals need to be clear, and the benchmarks need to be very clear as well, so that you know what you're actually targeting. Next slide, please. Just wanted to touch on concrete maturity sensors, since it's somewhat new in our region. It's something that's been used for years in tracking heat in mass concrete pours, but in our region, we haven't seen a lot of the full potential of maturity sensors in concrete pours. And really what we're talking about is little sensors, temperature sensors that can go in a concrete pour and wirelessly beam temperature history data that can be calibrated and worked out ahead of time and monitored throughout construction to really gauge in-place strength. The temperature history of concrete gives you what they call a maturity index, and that's tied to the strength of the concrete. So it's a way that we can more optimize our cement content, because if we know the actual in-place strength of concrete and we're less reliant on cylinders and the time it takes to collect and break and report cylinders, maybe there's an opportunity to eke out a few more hours of concrete curing at no real cost, and provide some additional measure of schedule certainty. It's something that our Chicago office has a few years of experience extensively with the use of maturity sensors. It's not something that the design team specifies or requires of the contractor, but it's something that our specifications allow for. If the contractor would like to use this method, it's covered by ASTMs. It's in use across the country. It's a viable way of doing things. And the quote that my colleague in Chicago said, that once contractors use this method, they don't go back. And we've seen a lot of local excitement on this front, but not a lot of local implementation yet. Next slide, please. I wanted to end with just two quick slides about implementation, because this is embodied carbon reduction in our region is, as a targeted project goal, is very, very new. West Coast has been doing it for years. They're good at it, but they're still learning. our region, it's very new, and there's not a lot of, or at least as of a year or so ago too, there wasn't much data in EC3 for our region or any at all. And now that's starting to change. But one project that I just wanted to highlight is it's an office building. It's a case study where we did, it's a post-tension slabs. The project started with embodied carbon reduction goals, pretty aggressive goals set by the owner. The contractor is using slag in the post-tension slabs, major cement replacement at mass foundations, at the mild steel slabs, at vertical elements like shear walls and columns. And what we're seeing is 30+% reduction in terms of embodied carbon on this project. And so it's very exciting. So next slide, please. And the strategies that we used for this, and again, these are topics that I think this forum is going to get into in much more detail in future sessions, and I think the whole region is going to be excited to learn from each other as we go through this in the future. But the keys were early collaboration with the owner, the contractor, the architect, the sustainability consultant, with us as the structural engineer, replacing cement where possible, where it made sense, allowing longer cure times where possible and where it made sense, using CarbonCure, using this incredibly innovative product that admittedly it showed up on a couple of Thornton Tomasetti projects 4 or 5 years ago, I think, and we didn't really realize it was there because it showed up in the mix design, but we didn't really question what it was 5 years ago. Structurally, as a structural engineer, I didn't know what CarbonCure was 5 years ago, and it's got no adverse impacts on the structure. It was being used before we knew it was there, and now we're allowing for its use in all our projects, and that it's one more tool in the tool belt, right? And then using concrete maturity sensors to gauge in-place concrete strength. And then this project also required the generation of EPDs for the mixes, which was something that the subcontractors had not done or had to that point. And with concrete, right, you can pull so many levers during your mix design that almost every mix can be different. And every mix is optimized for the project. And this way, the contractor was able to do trial batches and do their mix design and come up with the best solutions they could to meet project schedule and meet everybody's requirements. So in my mind, this has been so far a great success story and a good jumping off point for the region to show what can be done. And with that, I'll sort of end there and just say that I'm excited to be part of this group and to continue the conversation on how we achieve lower embodied carbon, not just for concrete, but for other materials. And a lot of it happens through design, specifications, and then in the products themselves. So thank you.
Thank you to all our speakers. Does anybody have any questions that you'd like to post either in the chat or unmute yourself?
Yeah, this is Lauren Wingo. I posted my question in the chat, so I'll ask it here now. Thanks to all the speakers. Those were great presentations. I had a question about how we as an industry could set appropriate benchmarks local to the DC market. I think, Michael, you touched on this about different approaches that we could all individually do within our firms, but probably for Tech's benefit, it would be nice to have a more universal benchmark for the DC market so that when we're writing performance-based specifications, we're holding to the same standards. And currently in EC3, because we don't have local EPDs, I'm just curious what your thoughts are on how we can approach that.
Maybe I'll start and then let others chime in, but we ran into this exact problem, Lauren, with nothing in EC3 or very little in EC3 at the time. There's not a lot of, you can't just say, all right, all the Vulcan plants and all the Superior plants within 20 miles of DC, we can look at these averages and benchmark things this way. And I think the biggest key here is hopefully starting with, I think we have to start somewhere, right? So I think, in my opinion, we've got to start with the NRMCA regional averages for our region. Start from there, and then the key, I think, for the whole embodied carbon push, and others can disagree, but the key is data, and we don't have enough data right now. And what all projects should be doing, and it's part of why the Structural Engineers 2050 commitment is out there too, is to start tracking embodied carbon, start getting the information. And if in the DC market we can start building up a database of what's been done, then we would have more data for our market. And what that's going to show, I think, is if you take the NRMCA averages for the East region, we probably can beat those pretty well right now in the DC market, especially by doing some of the things that Teck is able to do and other things. But after that, it's, all right, as we start to beat those on projects, our benchmark is going to keep getting lower, right? Then we're going to have to keep improving. So some of it is on the mixed design side, but some of it's just on the design side. So from a total project embodied carbon, are we able to, for a generic office building, is it 300 kilograms per square meter average? Maybe that's what it is right now with the lack of data that we have, but maybe in 10 years it's 200 because we've gotten more data and we've made advancements. And then your reduction target isn't, well, let's beat 300 by 30%. It's all right, we got to beat 200 by 10%. But those are, Lauren, I think it's a great question. It's something that we all struggle with, and I think the local market and the industry is going to continue to have to work toward as we move forward. So those are my thoughts, at least as of right now.
I like to contribute my thought on that question. The benchmark NMCA come up with is really, if you're limiting it to a DC area, for example, the sample size will be very, very small. And that gets, from a statistic standpoint, I don't know what it really tells you. I believe what a benchmark, when you have a statistical survey, you take a sample size and you say, okay, well, the sample is going to represent the population, meaning what is possible, you know? So nationally, what is possible is one thing. Regionally, the East Coast, what's possible is another. But when you say, well, what's possible in the DC region, you know, there aren't that many producers in the DC area. There aren't that many ready-mix producer plants in the DC area that can fit into, you know, you really have to take a survey of every concrete plant to create a big enough sample size for the statistics and for the benchmark to mean something. So if you just limit it to the DC area, then, you know, well, Vulcan is going to be competing with Superior and competing with, say, Miller Long on-site plant and, you know, Titan and stuff like that. And we all use pretty much the same material. I mean, the tools in my toolbox that are available to me is available to everybody else. And, you know, what do we end up competing with? You know, do I use more slag in this mix and compare with, say, from Superior? And I mean, at the end of the day, you know, the purchasing decision by the general contractor and the owner selecting the supplier, there's a lot more to it than just the EPDs for you know, for the project. And so the targets, I think a regional benchmark is already more restrictive than by nature than a national benchmark, but you know, we're achievable. Perhaps, as Michael was saying, it's we got a lot of statistics, and to look at 10 years down the road, maybe that's what we end up with. You know, every concrete plant in the DC region will have its own EPDs and stuff like that, and then we can start comparing apples to apples and so forth.
And Teck, I think it's two sides of the coin too, because we're talking about the concrete mixes themselves, and mix by mix, what are the benchmarks and what can we achieve? But it's when you look at the project as a whole and on an overall project basis, and a lot of that then goes back to the design and what's the architectural grid, what slab thickness are you using, what combination of thickness versus strength are you using. The design holds a key to reducing embodied carbon to a great extent as well, because if you set yourself up from a bad design, we can throw all the slag in the cement or in the concrete as we want, but we're reducing from something that should have been much better to begin with.
I think I was just going to say too, I think Lauren, you know, as Michael and Teck are saying, we don't have the data yet to really kind of drill down. What's the easy first step? You do know the cement content of the mixes, right? And the first thing to do, in my opinion, is, you know, you talk to Teck, you talk to Mike Tornquist at Superior, talk to the others and ask them, like, this is what our project objective is, and these are the mixes we're going to need. What tools do you have to help me cut cement? You know, like what is in your toolbox? What can you bring me? And most projects aren't doing that yet. So, you know, most of the time people like Teck and Mike are locked in a situation where, as Michael said, maybe the design wasn't great to begin with, and now they're locked into giving you something and there's no time left to change that specification. So something to consider there is just, you know, like what options do you have up front, and do you know what opportunities there are? And I think what you're hearing Teck say in this presentation is there's lots of options locally. Most of the time, or not maybe most of the time, but some of the time they're not being used when they could be.
This is Julia Seipel. I'll jump in with a question here. This is a really good conversation, and I appreciate the mix of the representation of the discussion here too, and with the design side and product and the mix. I guess I was very interested by some of the examples and talking about where jurisdictions are able to set policy goals and start to see success that is no cost add by making carbon improvements. So that Portland example, for example, how we're able to cut carbon with a certain goal that doesn't come with a cost associated with it as well. So I guess that's, to some extent, a question for our region is how do we start to set reasonable goals towards improvement that don't come with costs? And then from there, what can we do to still be flexible and keep the market open for further improvement?
The key success in Portland and in Marin County and other places is that, again, the concrete producers were at that table at that conversation. So when you start talking about baselines and goals, like understanding what the current reality is really critical. And again, I think as Teck showed in his presentation, things like slag might be more expensive locally than cement. Things like fly ash might be cheaper. So when you look at things in terms of an option that would be cost efficient, understanding your local condition is really important. Like I'm really concerned about people who just say things like, oh, I'm targeting, a 20 or 30% carbon reduction writ large. And I haven't actually thought about what the local situation is. I'm just copying what Portland did or something like that. And that's just really a challenge. I think, again, the incremental approach and really making sure, as what I hope you took away from this presentation is that concrete is very complex. And so taking kind of broad brush strategies isn't going to help. In fact, it might actually hurt. So I think that's just the key to success that I've seen, is that the jurisdictions that are thinking about this aren't really fixated on these hard and fast thresholds and reductions. They're fixated on what is an enabling environment that will help get things to the market quickly, and that are things that are affordable that we can start with today.
Yeah, and this is Christian. I work at Department of Energy and Environment in DC, or at least I did until today, where I'm moving. But I can tell you that within the region, both in DC and through the other offices in the region, through organizations like the COG and other regional organizations, the appetite is there. They're looking for examples of what to do. Very few people are experts on this, and every region is different, as we've seen today. And so I think people are very interested in this landscape. It's moving very fast. And I think there's going to be some pilot programs and looking to what other jurisdictions are doing and trying to figure out some good first steps, because a lot of people want to get involved at the policy level and just don't know where to start. And so I think that's something where an organization like this can actually help reach out and start those discussions as well, and kind of like point them to those pilot programs and say, why don't we do something like this? Or here's an option, let's get the conversation started. So I think there's definitely a lot of opportunity, and like you see in Marin and Portland, like these things are just starting in a few places in the country and in the world. So it's kind of early days.
Christian, it was great to have you as like the direct connect to DOE, and so congrats on your new position, but kind of in the absence of your direct role in this group, I think any perspective on what that means in terms of what's happening with conversations in DC and where those new kind of best connection points are with these discussions and what's happening at the kind of citywide level. If you have any perspective on who's kind of filling your shoes, or how their connections are in your absence.
So I've reached out to a number of my teammates. We've had a lot of discussions internally about embodied carbon and different potential policies, and to get some kind of, there's going to be a new roadmap being developed right now for DOE around a lot of these issues around carbon. There's kind of some shifts from energy to carbon within the industry, and within DOE as well, where people in the past have typically focused a little bit more on the energy side, not as much on the carbon. They're realizing that's really a place to reset our focus. So I was hoping some of them would join today. I don't think any of them are on the call today, but I do know that there's a lot of work there. They're closed an RFP recently for grants for people to explore in DC specifically low embodied carbon techniques, and to perform LCAs for early design decision assistance in that field. And that was just kind of like the first step of DC getting involved in that area. So I'll make sure that there are people from the regional policymakers involved with the local hub in DC, because I know most of them. So.
Thank you.
Does anybody have any more questions? We really appreciate everyone joining in, and thanks again to our speakers. It was a really great discussion. Appreciate it. Look forward to seeing you all in the next meeting.
Thank you much.
Thanks.
Thank you.
Thanks, everyone.
Thank you.